Today we are talking about the Fifo theory. Today we are talking about the Fifo theory and the RG, which is a relatively easy way of doing the RG by using the field theory method. So the idea is we can write down the partition function, right? For some bosonic field, which we say it's a Gaussian because it's quadratic. This quadratic in terms of phi, so phi is a bosonic field. So that's what we learned before in the previous class, right? So that's So when we start at the Gaussian theory. Which means the action is quadratic. So let's consider we have a action, and then consider d-dimensional action, and suppose it is translational invariant system. We can write everything in the momentum space. So this is the Gaussian form. Sorry, the field is labeled in K, and then I'm interested in integrating out from the smallest momentum, which is 0, up to a lambda. So lambda is some kind of cutoff, because as field theory, there should be some kind of knowing of the lattice, and then the lattice is the shortest length scale in the system, which corresponds to some kind of cutoff in the momentum space, which we specify as a lambda here. And since it's quadratic, we call it a Gaussian theory. Okay, quadratic. So this is the momentum cutoff for sure, like I said, momentum cutoff. Okay, so the RG, what is RG meaning here? As we learned from the IC model, that's putting everything on the lattice, we know how to integrate out the lattice, right? As before, wait a second, I want to see something. Standard. Okay. So RG. So what we did before is the real space RG. Space RG. Integrate some lattice scale, degrees of freedom, right? So which some kind of we are considered some kind of short length. Integrate out, which corresponds to integrate out short distance degrees of freedom, right? So if you want to do the momentum space RG, the short wavelengths will correspond to large momentum degrees of freedom, which we need to integrate out. So the idea of doing the momentum space RG, which is the same spirit as doing the real space RG, where we integrate out some kind of high energy mode, still integrate out the high energy mode. So in this case, the high energy mode corresponds to the large momentum degrees of freedom, right? So that's pretty clear for the setup. So the idea is we need to somehow do something in here, right? And then integrate out some of the high energy, which is the large momentum mode. This is the idea. And but before doing that, we need to simplify the questions. So as you know, in a rotation invariant system, we basically can replace this d-dimensional integral into a surface integral times a small distance, right? So this is basically, this is the corresponding surface for solid angle. So this is some kind of 1D. You integrate out something like this kind of d minus 1 dk. And this is the corresponding solid angle in here. Right, in d dimension. So this is something like I'm drawing pictorially. Okay, so far so good. So the solid angle, of course, in d dimension, it can be expressed in terms of, 2 pi d over 2. So now we simplify the integral, consider rotational invariant system. On the other hand, for this kind of d-dimensional setup, there's another advantage. So what is the advantage? The advantage is in principle, d belongs to positive integer number. For example, 1-dimensional, 2-dimensional, 3-dimensional system. However, if we relax this condition of the d, suppose it becomes relaxing the condition. And then suppose dimension can be a continuous variable. So suppose we can treat d as a continuous variable, then we can do some kind of expansion. Then we can do expansion such as, suppose I have a small variable epsilon, which is 4 minus d. So this is a typical called a 4 minus d expansion in here. Okay. So for example, if this is a function of d, if we treat d as that can be a continuous variable, then all the integral, we can put d as a continuous variable and then do order by order expansion, and then ask about d equals to 3 dimension, or d equals to 4 dimension, or very close to 4 dimension. What does the physics change? So this is a typical examples that we don't know how to solve the problem exactly, but we can do some kind of extrapolations of something we don't know. So for example, we can solve some system in 3 dimension, in 2 dimension, in 1 dimension, but we cannot solve in 4 dimension. We can basically extrapolate the behavior of some kind of correlation function or some kind of observables in d equals to 4 by consider d is a continuous variable. That is the typical idea. There's a lot of way to do it. There's other people did some kind of this kind of expansion, but treating dimension as a continuous variable by other application. So in general relativity, someone can do 1 over d expansion because, as you know, relativistics is not an easy object, but you can do if you treat d as a continuous variable, then sometimes you can get a more general form and then solve some kind of a weird dimension general relativity. Okay, so this is just a typical concept or mathematical tool that we often use in theoretical physics, treating d as a continuous variable and then doing some expansion and try to extrapolate the dimension with a certain dimension that we are interested in. So this is just a quick comment. Okay, so now as we introduced the RG scheme, we need to integrate out the high energy mode or the large momentum mode. So we need to split the field into two different modes. So let's suppose there's a slow mode, which we denote as a quantum field phi labeled by k, but k must belong below some kind of s. So s is greater than 1. So here I'm drawing something like this. This is my momentum k going from 0 to lambda. So this is the corresponding slow one. This is the corresponding fast one. And then this one is the slow mode of the momentum ki sum. Okay. So I also have a corresponding fast mode, which will be the rest of the interval. Okay. So that's pretty much I have. Then the action can be split into two modes. We call it a bare action because this is a simple action at this point. So we just repeat some things writing in here. It's function of k. So just a rewritten. Just splits the integral into two integral. Nothing changes. Nothing's changed. Right. So this is just a first. Okay. So far so good. Okay, no question at this point. Okay, so integrate out the fast mode. So we need to integrate out this part. Integrate out, right? Which is nothing but a number. So as you know, this is nothing but a number, which we call it's just like a partition function. Okay. So to be precise, what we need to integrate is the original partition function also need to split into fast and the slow mode. So let me write down the slow mode and then the fast mode, which I need to, okay, let me split this into two parts. This will be the fast mode. This is let's label it's the slow mode action, which we defined in the previous page. And this is nothing but the fast mode action, right? And since this is a Gaussian integral, this is just a number, and then we just define this number as the partition function of the fast mode. Okay. So now, as a result, in terms of the slow mode, you have an additional term if you absorb the constant into the action. Okay, so we can think about this part is the effective action after you integrate out the fast modes, which is nothing but same as before, but with a constant shift. Same action as before, but with a constant energy shift, which is minus log CF. Right. So constant shift doesn't change the physics. So as you know, this is non-interacting theory, which is quadratic bilinear in the field. So of course, there's no scattering between the fast and the slow mode. So the fast mode cannot give any weird contribution to the slow mode one. Okay. So this is showing there's nothing really interested here, as we know here. However, as we did the RG for the IC model, we need to do rescaling. So integrate out the high energy degrees of freedom. For example, in IC model, the short distance lattice degrees of freedom, and then we rescale. And in this case, in this Fifo case, we need to integrate out the large momentum degrees of freedom, and then we also need to do rescaling. So next step is rescaling. So rescaling meaning in here the integral k slow, or we label by k slow. Okay, so as you know, the remaining momentum is belong to here. So we want to rescale it, which means the distance will be the same as before, which like what we did for the IC model, we relabel the sides 2 to become 1, 4 becomes 2. So we need to do rescaling. So we can define k plan, which will be the same as before. So you want to identify these two. So you know this must be S times k, right? Okay, so this is something we need to rescale to redefine the momentum. So that's what's just like in real space. We relabeled the site index site, right? So this is the same spirit as before. Okay. So far so good. So for after this rescaling, we know the action. So I want to use the black one. The action defined for the slow mode. Now we need to do rescaling. So after rescale, it will be lambda, right? But you need to relabel your k by k plan, and this is k plan. And then of course, k plan square. And then of course you have d plus 2 when you do this changes of variable. So in principle, you have a minus d plus 2 here. So this is the new term. That's when you do this change of variable here. And then you can put the field back, the slow mode field back with label by k plan, right? And also this original label by k, so it will be k plan over s. So this is the rewritten of your slow mode action, right? So to make everything as the same before, we need to redefine our field. To redefine the field, the slow mode field by S, right? So let's redefine the field labeled by k plan, which we can absorb the square roots of the original d plus 2 in each of the original stuff. So you see, this is the redefined field. Then the action has the identical form, right? So identical form. Okay, so in terms of the new field, it will be the same as before. So you will immediately get this result back. You need to redefine your field. Pretty much you have. So it's kind of a fixed point, right? As you know, if the action is the same as before, what we did learn from the IC model, it will correspond to a fixed point. So in this case, we find Gaussian. If we start with Gaussian, we end up with Gaussian, and everything's identical, right? So it's called a Gaussian. It is a Gaussian fixed point. Gaussian fixed point. Okay. This is now we are finding a trivial fixed point where everything is non-interacting. So as we demonstrate in the previous class that if it is non-interacting, high energy mode does not interact with the low energy mode. So of course, everything will be the same as before after you integrate out the high energy degrees of freedom. So that's pretty much we expect. And then we do have a name for this case. It's called Gaussian fixed point. And then in this case, we can, since it is a critical point, we can ask about the critical phenomena, which we can extract the critical exponents. So as we learn from the thermal physics, there's a lot of critical exponents we can extract from at the critical point. So one of the extracting the critical point. Sorry, critical components or exponents of exponents. So we call it eta from the Green's function. So as you know, since this is a quadratic, the Green's function in this case is nothing but doing Fourier transform in momentum space, right? In d dimension. So you have d is d minus 2 in this case. And then the definition of the critical exponents, eta, is on top of them, there's a correction term. So in this case, eta is 0 when it is at Gaussian fixed point. Okay. Now we can consider something away from this fixed point. So now, so the first lesson we learn from the Fifo theory is without the Fifo term, with just the quadratic term, it is a fixed point, and then the fixed point is characterized non-interacting physics, and of course you know what you are doing, and this is quite straightforward, and you can extract the critical exponent. So now we can ask if we add other terms perturbatively, what will happen for this fixed point, right? So we can add additional term, for example, all this term, right? So this is the term that we haven't added. So we can add this term and ask, how does the fixed point change, right? So this is the question we want to know. Okay. I guess the internet is not that good. Anyway, so let's just add this term and then study what's happened. Suppose we add other terms. Let's suppose this is just a perturbation, so we put this epsilon, and then we can do this integral, right? The linear term, and then the other term that we consider as a mass term here. So R not considered as a constant, so it's behave like a mass in the Fifo in the original theory. So remember before S0, there's a K square. So this is just like a mass term here. Okay. And then we add the cubic term and then also the force term. So this is the so-called Fifo theory if you consider the force, the theta force term, because it's characterized interacting. So one thing we can notice, this term doesn't change the physics too much because this term can be absorbed in the force term, right? If you do this kind of shifting. Okay, then you can get a phi q term from this one. So you don't need to, you just redefine this field. You can absorb the cubic terms in the original theory. So basically, that indicates we can neglect the cubic term. So let's first analyze the linear term. So as you know, this is the linear term, which after one RG iteration, since we are doing, since preservatively, we can somehow say that, so what I should write is, I want to do one RG step. And then I know I should end up with the new field operator and the new coupling constant for the linear term, right? That's what the RG meaning for. Want to trace the changes of the coupling constant. And as you know, in the RG procedure, we first fix the edge and then doing the renormalized field. So as you know, the renormalized field defined as 1/2 1 plus 2d. All right. Sorry. This should be something wrong. So what I want to say is the redefined field corresponds to the new field. As we know, the phi field is changed with a prefactor, right? Prefactor. So then, sorry. So if you look at the previous page, we know the old field times s 1/2 d plus 2 will equals to the original one, right? So I want to replace the original one by the old one after doing the RG, right? So let's just do this way. So this will be S1. So if I compare these two, I can read out the changes of coupling constant, right? So that indicates the new coupling constant after doing the RG will have this kind of shift. One plus d over 2 h. Okay, so this is the changes of your coupling constant. Okay, after just a simple analysis by replacing the original field by the new field, the rescaled field, and then you absorb the prefactor into the coupling constant, and that will give rise to the redefined coupling constant in the RG in the first RG iteration. And since S is greater than 1, as we defined before, as you remember, that's how we defined S, which is somehow a method to separate the fast and slow modes. So the S must be greater than 1. So if S greater than 1, which meaning H grows, H plane grows, right? So it meaning it is a relevant operator, it's a relevant coupling constant. Okay, so it will grow. Now let's consider the mass term, which is the quadratic term. So we can do the same thing as before, separate the quadratic term, the mass term, into fast and slow mode, and then since it's quadratic in the field operator, so we know how to integrate out. So this is the slow mode, and this will be the fast mode. Okay, so fast, slow. So as we know, the slow mode part we don't need to worry about because there's nothing we need to integrate out in this part. The only thing we need to integrate out is this part, and this part is nothing but give you a number, right? So it's just the same as before, give you a number which you don't care. It's a shift, right? So the remaining thing is you need to rescale of this term. So rescaling basically, right? So we did before for the momentum term, we need to redefine the k plane in here. Right. So k plane goes to s times k. So this is the same R0, and this is the rescaled field. So let's just put this square. And then you want to, sorry, this will also give you so there's something I'm missing here. So to be precise, there's a rescale, you will give a s to the power d from this part, and there's no addition. However, each rescaled field will contribute to a minus d plus 2 here, right? I'm doing something wrong. Should be d minus 2. Wait a second. So I have a d from this part, and then the rescale field, each one gives me minus d minus plus 2. So I think I should left with wait, there's something wrong. I need to check. Okay, did anyone find something is wrong here? Yeah, so as you know, if I naively put this in front here, then I will left with f s minus, and then this is something before R0. So if I define this is the new coupling constant, which is not the same as what I wrote from my note. I'm doing something wrong here. So let me check. Oh, sorry, I think I know where is wrong here. So this should be minus because I need to replace this by this one. Okay, and then this should be plus. Yeah, so this will be plus. Okay, so now we resolve the problem here. So that indicates the RG process, the new coupling constant, after integrate out the fast field and then doing rescaling, I end up with the new coupling constant R for the mass term, which is R plum. R plum equals to S squared times R naught. Okay, as we know, R S is greater than 1, which indicates this is also relevant. Okay. So we have two relevant coupling. One is for the linear one, another is for the quadratic one. And then let's check back, does this mass term, which is a relevant operator, make sense or not? So the easiest way to check is from the correlation function. As you know, the correlation function near the critical point is divergent, and the divergent behavior corresponds to the mass term correlation function. So, sorry, correlation length. So from the correlation length, we know it's divergent near the critical point, and then how it's divergent corresponds to the mass term. And as we know, the correlation length for the previous one compared to the new one, the RG iterated one, must be times how you rescale it. The rescaling factor is what we did for the real space. Like what we did in 1D, we put it as 2. In 2D IC model, we put it as square root 2. In here, we put it as S because we rescale the system. So the correlation length for the old to the new with the new one must times the S, right? And then as you know, this critical mass will be S squared times the original one. Okay, so just a naive dimensional analysis, you make this as a dimension order of 1 parameter, right? So you basically, you can replace S by R naught minus 2 squared here, right? Square root of 1 here. So, okay, so it basically end up with some kind of this kind of scaling, the order of 1. Okay. So what does this mean? So if I look this as a mass term, so it will be something like 1 over a zero mass term with a power 1/2 here, right? And this basically is the critical exponent for at the critical. So that is the divergence of your critical exponent has this kind of behavior, right? Minus mu. So you indicate mu is 1/2. So basically, that also gives you a critical exponent just for the mass terms with RG analysis. Okay, and then this this critical, this is another critical exponent. Okay. And then we can do a similar check, or we can get the same critical exponent from the Green's function. This also agrees with the correlation length obtained from the Green's function. Okay. No questions so far. So as you know, the Green's function in the momentum space, we have additional mass term here, right? We can do Fourier transform to extract the correlation length, because when you do we define the correlation length from the Green's function basically in the real space. So we get this kind of form if you do Fourier transform, and then from the definition of correlation length basically is just defined as the exponential divergence length here. Okay. This will be d minus 2. So now if you compare the Fourier transform form and the definition of the correlation length, you read out the correlation length is exactly what we derived before, which gives you the critical exponent, which is 1/2. So same as before, right? So now what we can do is we can consider another more weird situation. If we expand all possible quadratic terms in terms of the phi field, we can put additional mass term, the quadratic in momentum contribution, we put it as a, so what I'm saying is to consider all the possibility of something in front of the quadratic terms in terms of the field. And this couple in R can be a constant R naught, as we defined before, as mass term, or some kind of renormalized momentum term here, which is quadratic in the momentum K. And then we can also get the force term, etc. And as we discussed before, this has a rescaling like this one, which is relevant. And as you know, the quadratic in momentum term is a Gaussian fixed point, which indicates it doesn't change, right? Fixed point, as we know. And then of course, the higher order term, R4, will be this one, which is irrelevant. So irrelevant. So it will basically vanishing when we go to the low energy sector, or when we do the RG many times, it basically will become smaller and smaller. So for higher order term, they are all, these terms are all relevant. So I will plot. So or irrelevant. So you can put 6 term, which will be R4, something like that. Okay. So we don't need to worry about this term. Next, so we already analyzed. So that's just a quick recap. So first, we consider the non-interacting part, which the field only described with its kinetic energy, which basically is something like this, right? And then we know this is a fixed point, right? And then next we consider the linear term in phi, the additional mass term in phi squared, right? And then we find these two are all relevant, so it will keep growing. Now next we want to ask the most interesting one is the Fifo term, which is this one. This we need to solve. Okay, so far so good. Okay, no questions so far. So now we just do it. Okay. So it's very straightforward that let's start at the fixed point, which is the Gaussian fixed point in here, with additional mass term, which is this one. So let's just neglect the linear term for this action for simplicity. So we can put it back later, and then we will for sure. So this is the fourth term here. So this is our action, right? And then these two basically quadratic in terms of the phi field. So basically these two terms just as this form, right? And this is nothing. So let me write everything explicitly. So this is nothing that we write before, we written before. So this is this term, right? And this is the best. We need to write it down explicitly. So let me write in the proper way. So we put the 1/4 for letter because there's a counting for this 5/4 term. So we put 1/4 in front of the coupling first. Okay. So we need to consider the momentum conserved interaction such that we only need to integrate out the three momenta, which because of the delta function, so I'm lazy to write. So in principle, you can write all four momentum and then put the delta function with the momentum conservation. But in here, we can simplify it by just integrate out one of the momenta. So as you know, we must have a momenta conservation. So let's define the K4 is equals to K3 minus, sorry, K1 plus K2 minus K3. So the picture we have something like this one. So I need to use the different. So this is K1, this is K2, and then something else is K4 and the K3. So momentum conservation meaning K1 plus K2 equals to K3 plus K4. So K3 must be K1 plus K2 minus K3. So that's pretty much I'm writing here. And then, so this will be the outcoming. This is the ingoing. So we put outgoing with this star as a creation operator. So basically, that's what you have for your terms, interaction terms. So this part, non-interacting. Oh, this is not good. Non-interacting. And of course, this part is the interacting part. So we can also return as the SI in here plus the S non-interacting. Okay, so same as before, split the field into the fast and then the slow modes. And then of course your action will contain the interactions between the fast and the slow mode in the presence of this 5/4 term. So you basically end up with the action only contains the slow mode, with the action only contains the fast mode, which of course is the non-interacting parts of your theory. And then the last part is the interacting part in your theory, which the fast and then the slow mode has interaction. They're scattered with each other. So that is the complication or the interesting physics can arise from this scattering between the slow and then the fast mode. Okay. Okay, so what we need to do is we need to as I said before, as the same for the non-interacting case, we need to integrate out this term, right? The fast part. So let's just write down things formally start with the action. Sorry. Start with the action, which is integration of the slow and the fast field here. Right, and then we can group into two different groups. One is the non-interacting part, only contains the slow modes. So I should write something into the same notation. So this is nothing but what we can group here. Let me use this line. And then the rest, the other part is the fast part, right? So this is the action, non-interacting part for the fast field, and then of course minus the interacting part of the slow and then the fast field. So this is the part that we need to integrate out, right? So we just write down the action formally, and then now we want to integrate out in a way such that, so let me try to do some . So the idea is if we can integrate out this thing properly, the first mode properly, we can end up with something called effective action, only contains the slow modes. So that's basically the idea of the RG. So basically this is some combination of these two. Okay. So this ... we can write down things formally. So this is what we want to obtain to get the effective action, which is we can extract how does the coupling constant changes after you integrate out the high energy mode, which of course, if there's some interaction between the high energy and the low energy mode, it must affect the low energy mode that maybe increase or reduce the coupling strength in the low energy sector. Okay, so the ... here we can basically write, or let me try to follow my note. So this part, right, basically is nothing, contains the non-interacting part, right? Of course, it will just absorb inside, and then the other part comes from integrating out the first mode, which we just write down explicitly here. So this is nothing but the non-interacting fast mode. So I'm just writing everything explicitly. And then I want to do a trick by dividing this with these terms here. And then times this term here. So I did nothing but divide integral and then times the integral back, right? Okay. So the interesting part is if you define this object here, right? This is just a partition function with respect to the, so you can think this part is nothing but the partition function for the fast mode in non-interacting fast mode, right? So this is some kind of average of a measure here, right? So it's some kind of average of this object, this function. Right. So if you rewritten things in this way, this part is nothing but doing an average over the interaction term. Okay. So now the only thing you need to take care is this term. Right. This is the only thing you need to take.
老师，老师，那个如果你写太下面的话，好像它那个会挡到，我不知道是为什么，因为是不是
这样子的？
这样子最下面那边它会有一些会切到，我不知道为什么，蛮好奇，不知道为什么。对，我把 print screen 给你看好了。
哦，你不用理，我知道，你那个 full screen 你就不会被切到。
我有 full screen 啊。
那为什么
full screen 还是切？因为它有最下面会有一个那个什么参与者什么那一些有的没有的那个。
full screen 应该
还是我分享。
我知道你在说什么。Okay. Anyway, so
其他人有这个问题吗？
我的状况是我只要 full screen 下面那个视窗就会缩下来了。
你
有原始大小有这样可以了，就是说你那个这上面有个查看选项，那边有一个缩放比例，你那个用原始大小的话，就100%的话就不会了。好，那没事了。
Okay. Anyway, so what we know is this is nothing but a number, so we don't care. This is nothing but a non-interacting part which we can do it. So this part we can know how to do it. This part is just a constant. So the only thing we need to compute is this object, right? To get the effective actions after integrate all the decimal to extract the effective coupling. So how do we compute this expectation value of exponential? The idea is we can do this perturbatively because for any operator on top of the exponential, we can, for its expectation value, we first do the Taylor expansion, right? This is nothing but just an honest Taylor expansion, right? And then since each is an individual operator, we just get its expectation value directly. So this is nothing but this one. Right. And then we need to do some kind of re-returning by consider adding this term here, which the square is outside of exponential, and then so we basically add 0 back, right? So we can did in here as well. So we can add a exponential q minus exponential q. So what you get is you can basically reorganize this term, right? So this term is nothing but the original. This term is nothing but so if you put all this term back, this will be exponential value of a, and then you exponentiate it, right? So this is this term you can compute relatively easy, and then the rest term is the other terms you need to compute, which may be a little bit hard, but you basically you want to compute the exponential of this object, right? So square minus. So that's basic. So the idea is, the idea is you want to compute this, and then you can measure the term by term. So this will be the first correction term if you do the expansion. Yeah. So this can be computed directly, or I should not say directly, can be computed using Feynman diagram, which is a perturbative calculation, but you can compute it. Okay, so this part is okay, right? Sorry, I'm writing things wrong. So this terms in the exponential, so it must times. Okay, so as the result, that indicates this object we want to compute is nothing but evaluate the interaction part and then exponentiate it plus the same thing squared and then the exponential value squared term plus da da da. So the task we now is to evaluate this object. Okay, so now it's 3:30. Let's take 20 minutes. So let's start. So now we are trying to basically compute this one. So let's focus on this one first. Okay. So before that, as we know, at this point, we know the effective action after integrate out the fast mode is nothing but the non-interacting part of the slow modes. And then of course, the constant, this part, when we integrate out the fast mode, and then of course, this part, right? So basically, this is the effective action corresponding to integrate out the fast mode. Okay. So now we just need to focus on this object first, which we can do. We just directly integrate out the fast mode, which define the integration of this range of the momenta, right? So as we know, this is something like example 3, and then the I 2 pi d, right? Something like this. And then we have basically fast, slow, star, and then also fast, slow, star, so fast, slow. Okay, so this is the term we have. So basically, we end up with one term of phi 4, one term of phi s4, right? We get 4 terms of the cubic times the linear one, and then we exchange the fast and slow, right? And then we have 6 terms, which is the squares of both terms, right? Okay. The simplest one is we can do for this, because this will be 0, vanishes, because this is an odd term. So if we integrate out, for example, some odd power of the field, so this is the term we are integrating out, it will be 0, because basically it will have a perfect cancellation of the plus and minus term. So basically we don't need to we don't need to worry about this term, right? Okay. And then this term is nothing, but if we integrate out this one, it just gives you a number, right? And then this term is remains because there's nothing to integrate out of the, if everything is just contains the slope fields. Okay, so this term we don't need to worry too much. And we have 6 terms of this one, which 2 out of 6 terms vanish because of the U1 symmetry, which I indicate in here. So this is something like the superconducting order parameter, which is like a Cooper pair. You have 2 creation or 2 annihilation. If you measure with respect to a particle number conserved system, which is U1 symmetry, it will be 0. And then mathematically, it can be understood from doing this kind of path integral formalism. If you have something like z bar, so this will be z or z bar or z square, and then doing this kind of Gaussian integral, right? And then you can replace z in the complex plane with the polar coordinate, and then you end up with this one, give this kind of phase integral, which will become 0 if you integrate out all the phase, right? So the idea is this, in the presence of the U1 symmetry, 6 terms, only 4 terms remain. So which corresponds to fast, slow, fast, slow. So I label the part you want to integrate here. This is 1 term, and then we will replace fast. And this is the part you want to integrate. And of course, and this is the part corresponds you want to integrate. So this is the all 4 terms you need to integrate. So that corresponds to different momentum integral, right? But every integral is going from the energy shell. So basically this 4 gives the same contribution. So we just need to integrate out 1 terms and then times 4. Okay, that is a idea that you can do. So now we just need to label this 4 term, which is square times square term. I label 2 times 2. So I times 4 back. So I get U naught. So in the notes, I replace everything, all the momentum back with Ki. And then of course I need to put a delta function here. So K1 plus K2 will equals to K3 plus K4. And then I just integrate out this term, which is the slow K4, the slow K3, and then the fast K2, the fast K1. Measure in here. So you see I put a measurement in here. Okay, expectation value here. So this can be expressed in terms of the Feynman diagram, which corresponds to, I have some so I should plot sorry, in terms of label, I'm in that note, I put this as K2. And this will be K3. So the idea is I'm consider this as a Feynman diagram. I have a slow which I will draw in this way. I have a K2, which corresponds to this incident particle, and then I come out with a K4 momenta, and then there's a this corresponds to the slow mode, the incoming, and then the outgoing. So it will annihilate the incoming particle and then create an outcoming particle back. Okay. In this one, and this will be something like I have a ingoing K3 here, K to K1 here, and outgoing K3 here. So this will be 5s star 5f. So that is the picture I want to draw here. So this is just like a Feynman diagram by integrating out this loop. So this loop in here is what you are integrating out here, right? So as you know, this K3 and K1 must be the same momenta. So this indicates this Feynman diagram will be a delta function as a, so let me just put in this delta function, K3 minus K1, and then this is just a propagator, K3 squared plus R0, right? So this is the quadratic part of the fast field. So that's what we do the expectation value for. Okay, so we know these objects. So as the result, this term 2 times 2 will equals to, so after I integrate out the fast field, the renaming part is the slow field. So slow field, if I put K1 and K3 are the same, then K2 and K4 must be the same. So I just kill the 2 and 4 and I replace by the same K here. So this corresponds to the slow modes and integration, right? And then the fast mode part is the part I'm doing the integral, which is nothing but this object. I need to do the integral, right? So this is basically the terms that we can obtain. Okay. So we can write everything explicitly now at this point. So the effective action is nothing but the quadratic term, the non-interacting term, which is the K squared plus R naught squared with the slow field plus the interacting part in here, right? So I don't want to rewrite here, but basically this is part, sorry. This is the part that I want to put in here, which is the S 2 times 2. And then the remaining part is the fast the slow field one. So this will be the slow. So I will just label this in a simpler way. So this corresponds to the slow one. This corresponds to the integrated one. And then of course there's a remaining one, which is this square, which I haven't computed. So basically that's what I have. But let's focus on these three terms first, and then we will go back for this term. So this term is relatively easy. We can compute. So now after integration, we need to do rescaling. So we need to rescale two things. One is the momentum, another is the field operator. Okay, so now we can rewrite everything back, which is the first RG iteration. So, and then monitoring the coupling constant. So as you know, this is the first part. We know we did it before. So this, as you remember, it's a relevant coupling for the mass term. So this is the renormalized field. And then this, of course, is the interacting term, which the rescaling comes from so this S square comes from the just rescaling the slow modes. Right. So this part is clear. So this is nothing comes from the rescaling. Of course, you have this integration you want to do, but it just gives you a number, right? Depends on lambda. And then R0 and the mu0. So that gives you some kind of a function depends on lambda R0 and mu naught. And then we will evaluate this later. And then of course the rescaling of the fourth term of the slow modes. So basically this rescaling comes from this term, right? So you have a d minus d here, and then also the field term rescaling. So this rescaling basically is nothing but this one. Okay, and then with sorry, I'm writing things. So this will be a product of the k. Okay. So that's basically you get all the terms back. So this will, and then of course the part which we will come back this later. So this part is essential for the next order correction. So this is the same as before. We focus on this first. Okay, so the red. So this gives us the effective action, which we can also express in terms of the Feynman diagram. So the non-interacting part, right, corresponds to slow modes, which is a bilinear in phi field. So that is basically you draw. I'm always draw. I will draw like this way. So I annihilate one particle and create one. So it's a 2-point bilinear in phi field. And the interaction one, I can have a 4 fast field, which give you a constant. So I have something like a 2 bubble interact. So this gives you a number. So I also have a interacting 4 slow one. So you have in, out, so slow, right? Which corresponds to this term. And this term is just a constant term. So we already neglect in the previous one. And this term which is something that we drew before. We have slow, and fast, right? So that is the Feynman diagram we have. So this is tadpole diagram. Okay. So far so good. Okay. Okay. So let me just summarize what we have before. What we have now. Summarize. So it's Fifo theory for you to remember. So it's very quick. Fifo theory. As you know, this is a field theory defining the integral of a momenta with a cutoff lambda. And then we consider the phi field, which is a bosonic field. We written everything in the momentum space. So we need to define the actions, and then the action is defined on the momentum space. So the first term is the linear term, and then the second term is the quadratic term. Quadratic term has two components. One is the k squared term, which is the kinetic part. R0 one is the corresponds to the mass term, right? So this is the linear, quadratic, and then the Fifo term, which just writes something very quick of product over with momentum conservation. Okay, so what we learned before, Gaussian fixed point. Basically, which corresponds to mu naught and h naught is 0, right? So there's no this term, no this term, and no this term, right? Okay, only has this term. And then what we can know is we can integrate out the fast mode and then rescale the momenta, and then also the field. And then you can find the new action which is invariant. Which is a fixed point. Okay. That's what we learned from the Gaussian fixed point by rescaling this one. And then the second one is, now we add back the linear term. And then as we know, doing the same trick as the rescaling. We find this rescaling has changes of the coupling constant. After rescaling the momenta and the field, you end up with the relevant coupling in here, right? And then the third part we know is the Fifo term, and then we just summarize. You need to do this kind of when you integrate out the fast mode, you do have an effect on the slow mode, and then the corresponding Feynman diagram is this one. You need to compute, which is nothing if you write in terms of the measure is like this one. Okay, so that's what we what we learned so far, and then we want to ask how does the unit plan changes under the rescaling. That is our next step, and then discuss about its relevance or not. Okay, so to study the changes of the couplings, we can change the variable. S by exponential L. So remember S corresponds to rescale of the momenta, or the try to redefine your lattice size, right? The lattice level. So it's kind of change of the length scale. Okay, so we just changed. So this corresponds to change of length scale, right? So you can expand by exponential L for a small L such that you can do as infinitesimal changes of rescaling the length. Okay, in such a way S will be very close to 1, so we expand by 1 plus dl. Okay, so the changes of, okay, so this is what we can do for small changes of the length. So we can, if we have this in mind, then we can do the integral that we read before for this integrate down the vast mode for the bubble. So it will be K3 plus R0. So if this is just 1 plus dl, this is nothing but 1 minus dl times lambda, right? So this is very simple. And since it's just a small interval along some d, and then consider this is a translation, a rotational invariant system, we don't need to, we can replace this by a solid angle integration, which we can put as d out to 2 pi d out as well. So this would be lambda 1 minus dl, and then the rest part will be k3 d minus 1 d2 to the power d3 divided by k3. And as you know, this is just a small lambda dl times the rest of term evaluated lambda for simplicity. So this is nothing but u naught s d 2 pi d. So this will be lambda d minus 1 lambda squared. So this is k evaluated by lambda plus r naught, right? And then the rest part is the width, the small difference is d times dl, right? So this is just a integral you directly will get. So let me define all the constants by a, then it's nothing but u naught a divided by 1 plus r0 dl, defining the cutoff by 1. So I just rescale my largest momentum to be 1 in the system for simplicity. Okay. So now we can start from this one, and so this term is for small r naught, right? So free massless point. So this will correspond to massless point, right? This is nothing but this one, and then we can ask about how this changes the coupling constant. Okay, so the effective action. So we have a bunch of integrals. So let me put this in here. So the quadratic term, the bare one, the slow mode one is still like this one, right? And then you have the this part, right? Part is nothing but times a dl, right? Okay, so what I'm doing is trying to extract the changes of u not u0. Okay, so you know, oh sorry, of the that r0. Okay. Because this is only quadratic in phi field, so it will correspond to the r0 term. So if we look at this carefully, the first term is still k squared, and then s is 1 plus dl, right? So this will be 1 plus 2 dl r naught. So this is also 1 plus 2 dl mu naught a dl. So which, if we compare to the renormalized coupling constant r naught, should be something like r naught plumb, right? So we need to read out the changes of r naught from here. So that it will be the new coupling constant. Sorry, the r naught after the r naught after the first RG iteration. So the remaining part will 1 plus 2 dl. So there's 2 dl r naught plus a dl. We can do it order by order. So this is order by order. So we have a 2 r naught plus u0a dl. So this is the leading order in dl, and then the second order of dl squared, right? So you immediately sees the changes of the coupling constant with respect to the changes of the length scale is equivalent to. Okay, so remember, what is this? This is nothing but the beta function, which we defined for the Ising model before. For some coupling constant, we define something like change of the length scale, right? So as we know, now we define S as exponential sum of the L. So this will be L here. So the log of L basically replaced by dl here. So this is nothing but the beta function, right? And then you see it's the first order equation, first order differential equation. So it's a beta function. Okay. So far so good. Now we are consider. So we got the beta function of the R0. Now we want to get the beta function of the phi for the mu zero, u0, the quartic term. So quartic term, the Fifo term. So of course, the Fifo term is obtained by directly rescaling the slow modes, because we neglect the interacting square term, right? For our simply analysis, so this is called tree-level RG, because we didn't doing the first loop correction. So it's a tree-level RG, which means just rescaling. Okay. So as we know, this is nothing but expanding this by the L mu naught. So the beta function of the mu0, the quartic term, is nothing but still a linear equation. So we have two coupled beta function. One is corresponds to the R, another corresponds to the U. This is a quadratic term. This is the quartic term, defined in this way. So this is linear equation, so we can solve this easily, right? So obvious fixed point is K star, which corresponds to the coupling constant. So don't confuse it with about this K. This is not the momentum. This corresponds to the coupling variable, which corresponds to R star equals to 0, and then the mu star equals to 0. So you know, if we put 0 in here, it will be 0. Remind ourselves fixed point beta K equals to 0. So as you know, if you put this 0, it must be a fixed point. Okay. So after this is an obvious fixed point, which is the Gaussian fixed point as we discussed before. Okay, so now we want to ask about how does the flow or coupling constant behave just slightly away from this fixed point. Does it goes away, or it's goes smaller and smaller toward the fixed point? Okay, that is the next step. So to study this, we just expand near the fixed point. So define the R0 near the fixed point by small deviation, same as the U0. Okay, so you just get the chain rule for your coupling constant by derivative of the beta function with respect to R0. So you're trying to study the behavior of the changes of the coupling constant deviate from the fixed point, right? And this is, you can just directly use the chain rule to see how this delta and how this changes. So this is basically what you want to study. Okay, this is nothing, but so this you can evaluate this. That's one, right? So this is just written. It's as a flow equation. So this will give you 2 because beta R is nothing but this one. Beta U is this one. So partial derivative with respect to R0 and U0 and U0 basically give you 2A 0 4 minus D here. Okay. Which you can solve in the eigenvalue equation. Okay. So what do we have here? Something interesting we can directly know is this term. Two eigenvalues, which occasionally it's in the diagonal part. Values 2 and 4 minus 2. And as you know, this 2 comes from right? And then you remember by definition, this is 1 over mu, which we discussed in the previous lecture, the Ising model. So you can check this relation. So which, same as before, we get the critical exponent mu equals to 1/2. Now the eigenvector, which is something we can extract the flow vector, which corresponds to eigenvector 1, 0, which has eigenvalue 2, and then b is equals to minus a d divided by d minus 2 and 1, which is eigenvalue 4 minus d. So you see, this is very interesting because as we discussed before, we put this d as a variable here, which we can discuss later on. And then you will see different dimension, the flow is different. Okay. Okay, now we want to get the flow equation, which indicates we want to know how does the changes of the coupling constant are labeled by K alpha. So let's suppose in our notation K0 is R0, K1 is mu 0, K2 is H0, etc. So this is just a label for different coupling constant, which is couple equation. So we want to know how it's the changes of the flow, the velocity corresponds to the previous before the RG iteration. So it's what we discussed in the Ising model, which gives you the flow, right? So we want to translate this T, which gives you the flow, from what we discussed in this kind of differential equation, a linear differential equation. We can translate directly because this part is nothing but rewritten this as d delta k alpha dl, which omega alpha beta, right? So this omega alpha beta will correspond to this part, right? Okay. So so we can translate this. This is norm. So we can get the T, which is the flow equation we want to know. Okay, so at this point we know this is nothing. Changes of the difference of the K plane, which will be the after RG step, the changes, which is denoted by delta K plane alpha, right? So what I'm saying is this part, this d, small d delta K alpha is nothing but this one, right? So this small changes, so there's no problem here. So we can write this is this one plus d, right? And then this is nothing from the, so this is nothing but omega alpha beta dl times delta k beta, and this is k alpha. So we left out with delta alpha beta plus omega beta dl times delta k beta, right? So you see, you immediately get the relation T alpha beta from the omega alpha beta, which is this matrix. And as you know, this one, in terms of matrix representation, is just the identity. So, and this, you get the corresponding eigenvector A and B, which the identity doesn't change the eigenvector. So the eigenvector of omega will be the eigenvector of t. So we don't need to worry too much. The eigenvalue will change. So, but eigenvalue will change, but it's change trivially because 2 and then 4 minus d for the eigenvalues in omega will becomes, so 2 will becomes, so this is identity, right? Plus this is 2 plus dl, which is nothing but s squared, right? And this is nothing but 1 plus 4 minus d times dl, which is nothing but s4 minus d expansion, right? Recall we do this like this one, right? Okay, so the eigenvalue changes. So this eigenvalue corresponds to the eigenvalue. So sorry. So what I must change is the eigenvalue of this one is 2 and 4 minus d. The eigenvalue of this one will correspond to s2 and s4 minus d, right? So we have basically the eigenvalue equation. Okay. Okay, now we can also put another eigenvector back, which corresponds the linear term. Okay, we know the linear term as the scaling, which will be d divided by 2, 1 plus. Okay, so this is the flow equation we can get. This is from the scaling behavior. This corresponds to the linear term. Okay. Okay, so now we have we can analyze the coupling constant. So now for sure, it's forced in 2 parts. So when d is less than 4, so we can see. So let me mark this. So the d is in here. So d less than 4, then 4 minus d is a positive number. And then since d is always greater than 0, so we end up with 3 relevant couplings. So R0, U0, and the H0, right? Which everything will grows up. However, for d greater than 4, so this part will be growing smaller and smaller. So we have 2 relevant and 1 irrelevant. 2 relevant couplings, which is R0 and sorry, it's not easy to say in here because, as you know, it's a couple one. So in terms of the flow, we need to consider a flow in a 3-dimensional parameter space. So there's a linear combination of the coupling that is irrelevant, which will flow into the fixed point. And then we will see that in just a few minutes, okay? And then that reminds you the IC model where we have various of the coupling term, the nearest neighbor, the second nearest neighbor, and then the quartic term, right? So your coupling flow is a coupled equation. So it's just like a IC model we did before. Okay. So far, so good. So now we start analyze the d greater than 4 physics, which is easier because we know there's a irrelevant coupling will flow into a Gaussian fixed point. So the picture we have in d greater than 4, we have this kind of parameter space, which has R0, U0, H0. This is the Gaussian fixed point. So let's just focus on the H0 equals to 0 plane. So this plane you basically can draw the figure U0. And then this is R0. And then we know R0 is the relevant, and this is K star, the Gaussian fixed point. And then you know the R0 is the relevant operator keep rising. So it will go this way. And there's some linear superposition line which will flow in. Like this one. And there's other lines to follow in this direction. So that's basically the flow you have. So this line, as we discussed in the Ising model, should be the critical lines, where defined as all the flows going toward the fixed point. Okay. So now how to obtain the critical line, so which corresponds to the eigenvector B, right? So this part is correspond to eigenvector A, which is 1, 0. As you know, A corresponds to the delta R0, delta mu 0 basis. So this keeps growing and this remains 0. So it will goes out. Okay. Goes out meaning the eigenvector is greater than 1. Okay. And then this one, the eigenvector eigenvalue as smaller than 1, and then it will flow in. And then I want to understand this part. How does this change? So recall, B is nothing but minus A divided by D minus 2, 1, right? Which we want to link this to the changes of the coupling constant, right? Because this is how we defined in the couple equation. So basically, automatically you get this one, right? So you get minus AD plus 2D minus 2. So you get this kind of line equation. Okay, so this is the line equation. So I can erase this delta. So this is basically the line equation for the critical line. So that is the flow diagram you can obtain for this, corresponds to the green lines. Okay. And then then we are analyze at 0 equals to 0, right? So this is nothing. So we are now next is trying to understand the flow, not on the critical line or mu equals 0 axis. So I want to understand how does the orange line flows. So this can be choose as a random initial condition. Let's suppose here. Okay. So this random initial condition can be labeled as a vector, which will be R0 times 1 plus mu 0 times 2. So let me put a 0 in here. That's the initial condition, which is R0, 0, mu 0, 0 here, right? Okay, and then we ask how it flows. Okay. So recall, A is the eigenvalue 1, 0, and B, sorry, I'm writing things wrongly. Okay, so I'm trying to, so what is one vector here? So one vector corresponds to, so this is R0, this is U0. So the one vector corresponds to a unit vector pointing along the y-axis. The two vector corresponds to the x label is the x vector, unit x vector, which is pointing along the u-naught direction, right? So any point in here can be expressed in terms of this one, right? But the eigenvalue of the flow is given by A and B, which, as you know, A is nothing pointing along the same direction as the one direction, so we can label this one as 1. And then Tx on A gives the eigenvalue flow like this one. And B, of course, is the linear superposition of the 1 plus 2. So this is the 1 plus 2, right? And then Tx on B gives the eigenvalue 4 minus D times B. So the idea is we start with any point in here, and then we want to express 1 and 2 by A and B, and then act on T and then see how it goes, right? So we can just doing this directly, act on T, and then rewrite psi naught by A and B, right? So this is 2. So 2, if you linear superposition, you replace the vector 2 by B and A, it will be nothing but this one. Okay, and then you know how this T acts on this one and this one, right? So it will be nothing. So let's focus on T acts on A, which will give you R0. So Tx on A give you S squared times A, and then the remaining part is R0 plus mu 0 times A divided by D minus 2. Okay, and then the other part is the B part, which will be S minus D, B part, right? And then it's nothing but mu 0. So this is the second term here. Okay, so you can rewrite everything in terms of 1 and 2 again, which basically is the new point with respect to your new point on the R0 and mu 0 plane, okay? For a starting point at R0 and mu 0, okay? So this will label by Sorry, I should label by 0 as a starting point. So you get something like R0, 0. So you replace A and B by 1 and 2. So you get this one. S squared minus mu 0. Okay, that's 1. So this will be the new R01, and then this will be U0 as 2. So this will be your new U01. So which gives you the all the flows. So basically what I want to say is this is what you have for R0 and mu 0, and this is the fixed point. You have something like this one, you have something flowing here. So if you start at this R00, mu 0, 0, this one will give you another point, which will be R01, mu 0, 1.